Okay, let's talk a little bit about ionization constants for weak monoprotic acids and bases. If we look at an acid like acetic acid, which is weak, we get acetic acid plus water produces hydronium ion and acetate ion. So the equilibrium constant for that could be expressed as the hydronium ion times the acetate divided by the acetic acid and water. But we've already talked about that the activity of pure solids and pure liquids is 1, so we're going to leave the water out of the equilibrium constant expression, and so our K is equal to hydronium times acetate divided by acetic acid, and we're just totally going to leave the water out of it. And it's a common mistake for people to try to stick that water in, so don't do it. And so we're going to call that Ka. So for acetic acid, the Ka is equal to hydronium times acetate divided by acetic acid, and that's going to equal 1.8 times 10 to the negative fifth. Your appendix will have values of common weak acids and bases in their Kas or Kbs respectively. In the simplified form, we're eliminating the water from the hydronium. We just say acetic acid is equal to H plus acetate minus, and then so the Ka is H plus times acetate minus divided by acetic acid. That's equal to 1.8 times 10 to the negative fifth. We're just eliminating the water from the hydronium. So given that, if we consider that equilibria have products on the top and reactants on the bottom, that is, the bigger the Ka value, that is, the more products you have at equilibrium, which means it's a stronger acid. So out of all these, the ones with the smallest negative exponents are going to be the biggest. And so if you look at it, the HF appears to be the strongest, followed by the nitrous, then the acetic, then the hypochlorous, and then the hydrocyanic would be the weakest. But this problem asks which is the strongest, and so it is the hydrofluoric in order of their Ka values. So let's write an expression for the ionization of a weak acid HCN, and we'll write expression for its ionization constant, noticing that we had a 4 times 10 to the negative 10 for the equilibrium constant in terms of the number. So let's go to the paper. And so we got HCN, we want to write the equation for that. And so HCN, if we get that to dissolve in water, is going to go to H plus aqueous plus Cn minus aqueous. So our Ka, our acid ionization constant, is equal to H plus concentration Cn minus concentration divided by concentration of HCN. And then that is going to be equal to our 4.0 times 10 to the negative 10th. But that's the expression. So let's say we've got a weak monoprotic acid HA, and it's found to have a pH of 2.97. What's the value for its equilibrium constant? So we're going to have an equilibrium with HA forming H plus plus A minus, and we know the concentration of the HA is 0.1 molar, and we know the pH of the resulting solution at equilibrium is 2.97. And so that's all we know, so let's find the value of the ionization constant. I shouldn't have to do any fancy quadratic equations here, and I've transferred that information over. So we got initial, change, equilibrium, all these are molar concentrations. So we assume those are none. Now, I've got to have some way to get at these equilibrium amounts, but I do have a pH. So if we remember, hydrogen ion is 10 raised to the negative pH power of 10 to the negative 2.97. So my H plus is going to be equal to 10 to the negative 2.97. So that's going to be 1.07, we'll say, times 10 to the negative 3 molar. So now we got, so it's going to be 0.00107. And so we're not, oops, sorry. So let's look at this. And so we've got HA in equilibrium with H plus A minus, pH 2.97. I've transferred over the 0.1 molar. So if I set up my ice table where everything's in molarity, we assume those are 0, we're still going to need a hydrogen ion concentration that's equal to 10 to the negative 2.97. And we're going to need to run that through our calculator. And so we're going to get 1.07 times 10 to the negative third molar. Now that's the concentration of H plus at equilibrium. So that's going to be in a decimal form 0.00107. Now what we can say is that H plus gained that amount, and so did the A minus, because if I form some of this, I've got to form some of that because the equilibrium is shifting that way. Now, if I add over here, I've got to subtract here because I'm consuming the reactant to form the product. Now, what you're going to find is you're going to subtract that 0.010 minus 0.00107. And we're going to end up with 0.00893. So what you can see is that not much of the HA has ionized, which is why some people would say that that's approximately 0.1 molar. And now in some more sophisticated problems, we'll say that the amount, assuming the equilibrium constant is adequately small, we'll say that the amount is negligible. And so that'll help us avoid some of those quadratic equations. But for now, since we got the number, let's use it. Concentration of H plus A minus over concentration of HA. And so that'll be 0.00107 squared over 0.00893. Then you just need to run that through your calculator. And that's going to give me 1.28, we'll say, times 10 to the negative fifth. And so that would be our answer. So let's look at an example. We've got 0.15 molar acetic acid, and we want to know the concentrations of all the various substances. So looking at that, I've copied all the information over. Here's an equilibrium for acetic acid. Ka, if you look it up, is 1.8 times 10 to the negative fifth. 0.15 molar, none of that, none of that. Now, here's where we're going to apply that approximation I mentioned in the previous example. We're going to assume that I lose some of this, so 0.15 minus x, but I'm going to gain x of this and that. So that should look familiar. Now, looks like we're headed down the road to a quadratic equation, but if the ionization constant, regardless of which one it is, Ka or Kb, is adequately small, we can assume that it doesn't ionize very much, and so that this equilibrium concentration is approximately 0.15 molar, because X is so small it wouldn't show in the sig figs. That approximation certainly gets better as Ka gets smaller and worse as it gets bigger. But you can generally make that on a lot of Kas and Kbs, make that approximation. So if we assume that, then our Ka is going to be H plus acetate minus over unionized acetic acid, which will be, make that x squared divided by 0.15, which equals 1.8 times 10 to the negative fifth. Now you can see that I'm going to avoid the quadratic equation if I play my cards right. So then x squared is going to be 0.15 times 1.8 times 10 to the negative fifth, or 2.7 times 10 to the negative sixth. So x is equal to the square root of that. So we're going to take our square root, and it's going to be 0.0016 molar. Now that's the concentration of the H plus and the concentration of the acetate ion. And we know that the concentration of our unionized acetic acid is approximately equal to 0.15 molar. If you did it without the approximation, you'd see it's not going to make that much of a difference. So part B of that would be to calculate the percent ionization for that. But I've already done all the math, so really all I got to do is calculate the percent ionization. So using the numbers I've already got, how much ionized? This much ionized. This is the amount I started with, since I'm assuming that's more or less unionized. So the percent ionization is going to be the amount ionized, or 0.0016 molar divided by 0.15 molar times 100%. And so we've got a 1.1% ionization to 2 sig figs. Okay, now we're going to do a very similar problem with hydrocyanic acid, and we'll see the difference in the percent ionization, since the Ka in this case is 4 times 10 to the negative 10th. We'll still assume 0.15 molar concentration initially, and again we'll calculate the percent ionization for the acid. So if we look at this, it's going to work pretty much like it did before. None of those, plus x, 0.15 minus x, and we're going to assume that's 0.15 minus x. And then so that's going to be approximately equal to 0.15 like we had before, where this is x and x. So then our Ka in this case is equal to concentration of H plus, concentration of cyanide minus, over concentration of HCN. So that's going to be x squared divided by 0.15 equals 4.0 times 10 to the negative 10th power. See, it sets up very similarly. So x squared equals, so that's going to be 6.0 times 10 to the negative 11th, and we're going to square root that, and we're going to get 7.7 times 10 to the negative 6th power. That's equal to concentration of our H plus and our cyanide, where our concentration of our HCN we're going to assume to be pretty close to the initial concentration. It's even a better approximation since this Ka is a lot smaller. But now our percent ionization is going to be using this and this. So 7.7 times 10 to the negative 6 divided by 0.15 times 100% is going to be about 0.00516%. I mean, so it's much lower than the problem before. So looking at a summary table, we can see the acetic acid is a stronger acid than the hydrocyanic acid. It produces a higher H plus ion concentration in solution by a long shot. The pH is lower if you calculate the pH, and the percent ionization is lower for the HCN compared to the acetic acid as well, meaning that the 0.15 molar acetic acid is about 210 times greater than the 0.15 molar HCN, based on the content of the hydrogen ion in solution. Now, all the calculations we did are also work for weak bases. The only difference is that you're forming hydroxide in solution instead. And so what if we do pretty much the same thing except with ammonia? Kb is 1.8 times 10 to the negative 5th. And we're going to write our expression for ammonia reacting in water. And we should be able to get an answer. So all other factors being equal, we're going to write that, and we're going to produce ammonium ion and hydroxide ion. And we said that what the Ka was, and we said that this was 0.15 molar. So we're going to say initial change equilibrium. Since water's concentration is not going to change much because we're dissolved in water, we're going to ignore that column because it's not part of the equilibrium constant expression. But other than that, it works pretty similarly to the problems we've had before. And so we'll more quickly fill this in. And so now our Kb is going to be equal to the ammonium ion, hydroxide ion, divided by the ammonia concentration. So that's going to be x squared divided by 0.15. You see the similarity, 1.8 times 10 to the negative 5th. So it should work pretty much like acetic acid because the constant's even the same value. So doing our math, we find that again, x squared is equal to 2.7 times 10 to the negative 6, and so X is equal to 0.0016 molar, which is our hydroxide ion concentration and our ammonium ion concentration. And then our ammonia, we're assuming to be approximately equal to the starting concentration of 0.15. We're still making that basic approximation. So our percent ionization will work out the same. It'll be 0.0016 molar divided by 0.15 molar times 100%, or 1.1% ionization.